Okay, let me welcome everyone to the physics department, if you haven't been here before. And I'm Philip Stansel, the head of Department of Physics and Astronomy. And it's my great pleasure to welcome you to today's inaugural Chhabra-Landau Lecture. So I'm just going to say a few words before we get started. So this series of lectures is going to be an annual event starting today in our department, and it's established by generous donation from Dr. Chhabra. So I'll tell you a little bit about him. He doesn't want me to say too much, but he's currently the president of Euclidean Capital. He received his BS in physics from UGA, and he worked with Dr. David Landau, and then he went and got his PhD in applied physics at Yale University. After that, he was a postdoc at University of Chicago with Leo Kadanoff. He then switched to finance, in which he was the head of quantitative research at JP Morgan, and then he moved to Merrill Lynch. And then he established the Euclidean Capital, which manages investments for the Simon Foundation. So you may be familiar with the Simon Foundation, which is dedicated to advancing research in basic science and mathematics. He's also currently on the board of visitors for the Institute of Advanced Studies at Princeton, as well as other places. So let's welcome Dr. Chhabra, who's here for this inaugural event, and let him say just a few words.
So I'm Sharon Chhabra, and thank you all for being here. And I want to thank the Development Office, Dean Alan Dorsey, Department of Physics and Astronomy, the Center for Simulational Physics, for putting this together. I thought I'd just spend a few minutes and tell you a little bit about why we put this lecture series together. So, depending on your perspective on time, a long time ago, just the other day, I came from New Delhi to do graduate work in theoretical physics at the University of Georgia. And I received a really warm and wonderful welcome from a lot of people who lived here, so friends, faculty, and you know, I got a taste of Southern hospitality. And so I'm forever grateful for that. And over the years, I thought there must be some nice way to give back to the university, and thought about what would enrich the curriculum and experience of both graduate and undergraduate students, both in the Department of Physics and Astronomy, but also across the university. So came upon the idea of doing a lecture series, and I've always had a worldview that there's something deep about computing, and it's very much in the vein of those who are familiar with Eugene Wigner's article about the unreasonable effectiveness of mathematics in describing the natural sciences. I feel the same way about computation. There's something very fundamental about the act of computing. The energy it takes, the information it provides, is a fundamental insight into the way the world works. And so we thought about putting together a lecture series of interdisciplinary scientists, distinguished scientists, who use computers, computation, simulations, modeling, in order to gain deep insights into the world we live in, and hence the series. And then the last piece was, when I came, it was really the first piece of research that I did, and I did that under Professor Landau in Monte Carlo simulations. It was my introduction to Monte Carlo simulations, using the computer to do physics, and also how to do serious research. And I was very fortunate in subsequent years to work with very good physicists, including K.R. Srinivasan at Yale, Leo Kadanoff at Chicago. And you know, the fundamental training that I got working with Professor Landau really did sort of, in some sense, create the character of a scientist. And so, hence the Chhabra-Landau series is to honor also the hospitality that I got in Athens and the mentorship that I got under Professor Landau, who has created something very special here under the Center for Simulational Physics. And I hope that this lecture series will enrich that piece of work, as well as I said, the general curriculum of students at the campus. And I'd finally like to end by saying that I'm delighted that we have got an incredibly distinguished speaker in Sharon Glotzer. And we spent some time exchanging, learning more about the background, and I think you're in for a treat. So thank you very much.
Thank you very much. So I just want to show how active Dr. Chhabra was while he was here. So 4 papers for a master's degree. So just a hint for you graduate students. Okay. So we're really extremely grateful to Dr. Chhabra for establishing this lecture series. And so let me now turn to introduce the first Chhabra-Landau lecturer, which is Professor Sharon Glotzer from the University of Michigan. Dr. Glotzer received her PhD in theoretical soft matter physics working with Eugene Stanley at Boston University. So I'll say a few words about her. Her CV is rather long, but we'll cover some high points here. So after getting her PhD, she then was a national NRC postdoctoral fellow at NIST in the Polymers Division. And then she was the co-founder and deputy director, and eventually director of the NIST Center for Theoretical and Computational Material Science. In 2001, she moved to the University of Michigan, where she started as associate professor in chemical engineering and material science and engineering. And currently today, she is the department chair in chemical engineering and holds appointments in a number of other departments, material science and engineering, in physics, in applied physics, in macromolecular science and engineering, and at the Bio Interfaces Institute. She is a fellow of the American Physical Society, American Association for the Advancement of Science, and the American Institute of Chemical Engineering and Materials Research Society. She was also elected to the National Academy of Engineering, the National Academy of Sciences, and the National Academy of Arts and Sciences. She has a number of awards, but I just want to highlight 2 of them. Okay, one is the Aneesur Rahman Prize in Computational Physics, which is given by the APS. And you may know that Dr. Landau also received this prize in the past. And Dr. Glotzer also received the Maria Goldberg-Meyer Award, also given by the APS. So let's welcome Professor Glotzer here. I have a little something for you first. Dr. Landau and Dr. Ashton will come up, please. Have a little certificate, come over here. Oh. If you're in you 2 on either side.
My marks.
Maybe a couple of photos. You 2 on either side. Whichever side you want. Take some photos.
Over here, because I couldn't see it.
So that certificate and the virtual check is in the mail.
Virtual check. Let's get one. I'll crop cancel out, no worries. Great. Thank you.
Thank you. Thank you. This here. And that's up. Probably not, but I think if you're recording it, you want. Okay. Let's see where we can put it, because I have no pockets. That might work. Is that weird? There. You see it? All right, cool. Is it possible to turn the lights down? Oh, there it goes. It's beautiful. That's awesome. Thank you. Well, thank you so much. I am truly honored to be here and to help kick off this distinguished lecture series. I've known Professor Landau since I was a puppy. I can't remember when I met you exactly. but we're from the same community of critical phenomena, stat-nicky types. And Professor Landau has always been such a strong proponent of computational science. And in fact, when I was a graduate student at Boston University, I sort of grew up in the Center for Computational Physics there, which was founded based on the model that was set up here in the Center for Simulational Physics in order to support all of us who were doing computation. And so not only have you been such a strong proponent for computational physics, computational science in general, but also a really strong proponent, really strong supporter of young people in the sciences. And so I'm super grateful that you're still a supporter of mine, even though I'm not so young anymore. And I also want to thank Chhabra and congratulate both of you on this really wonderful thing for the department and for the community. So I'm going to talk about how my group is using computation to design new materials. From the Stone Age to the Bronze Age to the Iron Age, today in the Silicon Age, human civilization is defined by the technologies that we have and the materials that we have at hand help determine what those technologies are. And if we look forward and think about, well, what's going to be the next revolution, what is going to be the next kind of big materials transformation of our society, I think it's going to be materials on demand, which means materials that are designed and made for specific purposes in mind. And that means that we really need to understand a lot about materials and how they form what they form and how they have the properties, the structure and the properties, the behavior that they have. And computer simulation is an indispensable tool for helping to get at this very fundamental information about matter. And so I'm going to talk about what we're doing in this area, and let's see if this works. This works. But let's start at the beginning. All matter is composed of atoms and of elements that mix and match to produce structures, from very simple structures to very complex structures, from a salt crystal all the way to the human brain. And we understand, of course, that physical matter is held together by chemical bonds. We have chemical bonds between elements, and that's what holds stuff together. Chemical bonds result from the exchange of electrons between atoms, and we can explain them, the chemical bonds, by quantum theory and the wave-like nature of the electron. But it's thermodynamics that drives systems and materials towards states of minimum free energy. And its free energy minimization is why, if you take water and you put it in the freezer, it turns into ice, and why proteins fold from a denatured state into a natured folded state. Statistical thermodynamics exploits those interactions and then drives these systems towards a state of minimum free energy. And if you combine quantum theory together with statistical thermodynamics, then you can, in principle, determine all of the equilibrium structures in nature, in principle. Stable crystals can then be predicted if we know what the interatomic forces are. If we know what they are, we can model them, and then we can somehow minimize the free energy of the system subject to whatever the natural constraints on that system. Then we can predict all of these stable structures, including stable crystal structures. And quantum mechanics and statistical thermodynamics conspire to produce some really extraordinarily complex crystal structures. We hear a lot about, face-centered cubic, bicentered cubic, simple cubic. These are very common in metals, and those are really simple with very, very simple unit cells, very simple repeat units. But it's possible to get crystal structures, atomic crystal structures, with really large unit cells, hundreds of atoms large, thousands of atoms large. There are intermetallics made of 3, 4 metals mixed together that can have over 20,000 atoms in the unit cell. And then it repeats. And I find that just extraordinary. And among the greatest advances of the 20th century are the breakthroughs in quantum theory and electronic structure theory and the ability to predict atomic crystal structure by essentially solving Schrodinger's equation. And so we talked at various times today, we talked about these various electronic structure methods and these codes like ABINET and VASP and Quantum Espresso and others that, many of them are free, they're packages, they're used, very commonplace now in computational chemistry and computational condensed matter physics. And they use certain approximations of Schrodinger's equation to use and use some sort of iterative matrix methods to solve for the wave function and the electron probability density cloud, the bonding orbitals of a crystal, and the energy associated with that. And of course, the computational cost of figuring out what is the best arrangement, the lowest energy arrangement of atoms, the cost of doing that with quantum electronic structure methods increases with the size of that repeat unit, with the complexity of the crystal. But in principle, the chemical bonding structure of any set of n atoms can be computed with varying degrees of accuracy. And so that has become a transformative tool since the late 1990s in being able to predict electronic structure. But I don't work down there at that length scale. I'm interested in building blocks of matter that are larger than single atoms and larger than molecules that are somewhere between a few nanometers up to a few microns in size. And so that's down here so this is a nanometer scale bar, so between a nanometer and even up to 1,000 nanometers. And in this range, the building blocks of matter are larger and more complex. And so this is the realm of what we call soft matter, soft condensed matter. And these are atoms, which are very big and complex. So for example, gold nanoparticles, that could be anywhere from, 10 to 300 nanometers in size, that grow in solution, can be functionalized with all kinds of different molecular ligands, proteins, DNA. This is an example of a spherical DNA from Chad Merkin's group at Northwestern, where that can be a building block for a complex crystal structure, where the gold particles, if you say throw them in water, they have van der Waals interactions between them that are weak, they're there, but they don't necessarily want to order the particles into any particular arrangement. But if you have the DNA and the DNA wants to link these particles together and you've figured out what length of DNA to have relative to the shape of the nanoparticle, you can actually program in crystal structures, and I'm going to show you an example of that in a minute. You can, it's possible to make other kinds of nanoparticles and functionalize them with different sorts of ligands. You can make what are called Janus particles, where say you make a particle out of, like PMMA, polymethyl methacrylate, and coat half of it in gold. So that way one half interacts differently with other particles than the other side of it. And that builds in anisotropy and gives rise to more complex crystal structures than would be possible if it was a perfect sphere. Patchy, we call some of these sorts of particles patchy particles, whether they're at the nanometer scale or the micron scale. As long as you have particles that in some solvent are subject to Brownian motion and they're just getting kicked around and able to explore all of the possible microstates available to the system, all of the possible ways that they can arrange themselves, then that's a system that follows the laws of statistical thermodynamics. Polymers, dendrimers, DNA, proteins, micelles, virus capsids, or even the proteins within virus capsid is a building block for a virus capsid. But the virus capsids themselves can be functionalized and used as a giant atom to make larger structures. So our considerations are different because our building blocks are different and the interactions are different, and because they're big, we don't have a Schrodinger's equation that we can solve to put these together and figure out and just solve this equation that tells us what crystal structures are possible or even preferred. And also, of course, temperature and entropy are important on these scales. And so this class of soft matter building blocks can self-assemble into also crystal structures of extraordinary complexity, many of which are isostructural to atomic crystals, meaning there's an atomic crystal where the atoms are exactly where the big particles are. Of course, the lattice spacing is much bigger for the nanoparticles, but they sit on the same lattice sites. And so here are some examples from various groups. This is an example, I think, from Dmitry Tolopin's group at Chicago, where they have different mixtures of, like a binary mixture of different size spheres that self-assemble into these very interesting and complex lattices. And these are, I think these are all spherical particles that are made of, they can be made of iron, lanthanum, fluoride, rare earth. This is an example from Frank Bates's group at the University of Minnesota, where he made triblock copolymers that self-assembled into big micelles, and the micelles now act as the atoms, and every one of those dots is a micelle comprised of many, many polymers, and they self-assemble into this very interesting structure. This is a picture from Pei-Yang Yang's group at Berkeley, where it's colored just to help you see what kinds of complex, what the structure looks like, or what the unit cell is. All this is several unit cells. These are silver nanoparticles that are about 50 nanometers in size, and they can self-assemble into this structure that's called, it's isostructural to high pressure lithium. It has 16 particles in the repeat unit, in the unit cell, and it's like an interconnected lattice. And then these are examples of crystal structures made from DNA-coded nanoparticles. It's also possible now to take nanoparticles and connect them to DNA and use the DNA to make this sort of scaffold and place these nanoparticles wherever you want to place them. And in every one of these cases, the interparticle interactions, as they're mediated by the solvent that they're in, and combined with statistical thermodynamics, are what dictate the crystal morphology. So principle, if we really understand all those interactions, and we can minimize the free energy, then we can predict what will form, and then ideally we could also work backwards and say, I want this function or this property, so to obtain that, I need this structure, and to get that structure, I need these interactions, or these shapes of particles. And that's where we'd like to go, is to be able to design that on demand. So here's an example of, just to show you what we're talking about, is that this is a giant, these are a bunch of giant crystals that are just false colored to make it pretty. Each one of these tiny, whiny dots is a gold nanoparticle. So this is a big crystal of gold nanoparticles that are self-assembled with DNA. So this is called, we call it a colloidal crystal when it's made of nanoparticles of colloids. It's a colloidal crystal of gold nanoparticles where the gold nanoparticles are arranged in a face-centered cubic crystal structure. That's what they like to form. But really, each one of the gold particles looks like this and is functionalized by self-complementary DNA that finds the end, the sticky self-complementary end of another nanoparticle and pulls them together in just the right arrangements, and the thermodynamics minimizes the free energy, and you get that FCC crystal. But if you look inside the gold nanoparticle, the gold atoms are arranged in a face-centered cubic crystal. So you have this really beautiful hierarchy of scales that's possible with colloidal crystals. So here's an example of the most complex colloidal crystal that I'm aware of that's been published to date. That comes from, again, from Chad Birkin's group at Northwestern, and that is a clathrate colloidal crystal. So clathrates are crystals comprised of water molecules. And they typically form, they're a hierarchical cage-like structure, and they typically form with big ions in the middle of these cages. And they can have very large unit cells. This one has a unit cell of 123 particles, gold particles. Here, they use this shape of particle, which is take two regular tetrahedra, and stick them together, and then squash it. That's the shape of this particle, and then they functionalize it with DNA. And we got involved with this because at some point, I remember back a few years ago, Chad texted me these pictures like, oh my God, what is this? It's so cool. We got this really complicated thing. Is it a quasicrystal? And I said, no, it's not a quasicrystal. Because I've been telling you for a long time, if you would make some bipyramids or tetrahedra, and I'll show you one in a minute, you might be able to make a very interesting quasicrystal. And so that's what they thought, and then they sent us the pictures and we analyzed it and made a model of this, and then did molecular dynamics simulations, and was able to show that they actually have this clathrate structure that I'll show you more about the structure a little bit later. But with our model, we were able to predict exactly the same crystal structure. And in fact, if they change the length of the DNA and nothing else, they can get different clathrate crystal structures. There's different kinds. And in our model, we can also do the same and get the different crystal structures that they get. So this is a really complicated colloidal crystal structure, the most complicated one that I know of so far. Now, from a simulator's point of view, these are really challenging systems because they're messy, because there's a lot going on. Here's a list of examples of what the nanoparticles might be made of, and you have all these different kinds of quantum dots and all the different shapes, and you can have magnetic nanoparticles, hard magnets, soft magnets. So here's all the different kinds of combinations of elements that can give you different kinds of nanoparticles with different properties and different shapes. And then in order to stabilize the growth of these nanoparticles as they're growing from ions in water, you throw in some kind of small ligands or surfactants that stick onto the surface of the particles and stop the growth. And in fact, it's possible to get a really low polydispersity, like polydispersity in sizes of only 3% or something like that. So you get a very nice, almost perfect distribution of sizes that way. But then, so those ligands then that you have on there, they have all kinds of, there's all different kinds that you can use as well, and they all have different kind of interactions between them. And so we have to think about van der Waals interactions between the particles and the ligands and the ligands and the ligands and the particles and Coulomb interactions and magnetic interactions and hydrophobic interactions, because many of these things are self-assembled in water. You can have ligands that can form hydrogen bonds, and then of course there's the excluded volume, which we're going to talk about. Just the fact that the particle has some shape and they can't sit at the same exact place. Right? And so we have all these interactions to think about. So when we first got into this game, let me put this here. So down here, when I got my PhD, so this is where this was chartered in 1986, the Center for Simulational Physics. And so you could extrapolate these lines. So this is from the top 500 list, the top 500 fastest supercomputers on the planet. Every 6 months you enter, there's a competition. The middle curve are the fastest, of the very fastest one of the top 500. The bottom line is the slowest of the top 500 supercomputers. And then this is the sum total. If you could hook up all of the fastest 500 computers on the planet to solve your problem, that's how much, that's how many flops that you would get. And so this shows down here where when I started working on these kinds of problems in like 2002, 2003, between then and now, there's been a factor of 1,000,000 in speed up. So generally you get about 1,000 speed up per decade. That's the general rule of thumb. So there's about 2 decades, so that's 1,000,000 times, things are 1,000,000 times faster now. So what used to take 4 years when we started, now takes 2 seconds. What used to take a day takes 90 seconds, or we can put much more detail, much higher fidelity models in our computer simulations, and put much more detailed physics in there. And so this is one of the ways that computational physicists are keeping up with these complexities in the experimental systems. And so when we first started working on these problems, I was collaborating, and still do of course, collaborate with my colleague, Nick Kotoff, who is a chemist who's also in chemical engineering department, like I am. And he makes little CAD telluride nanoparticles. They're semiconducting nanoparticles that are, oh, thank you. I have to say the service here has been fabulous since I got here. They're shaped like little tetrahedra, actually kind of truncated little tetrahedra that are about 1.5 nanometers on an edge. And he can coat them with different ligands. So he can coat them with DMAT or TGA. He can coat them with positive ligands or negatively charged ligands. And depending on what he uses, he sees in his transmission electron microscope different kinds of structures. So here's an example of nanosheets that form from these shaped particles here, where they're all basically just covered with ligands that are sticky to other ligands. So they're just coating them with sticky patches on all the sides. If he changes the ligand type, instead of getting these 2D sheets, he could get these long cubed wires. If they use the same thing as they do here, but they do it, they do the experiment with light, with the lights on, and you get these gorgeous, in between a 2D sheet and a wire is a ribbon, right? And so they get these ribbons, and then those ribbons build up stresses and they twist. So they have these long helical things. What happened? Uh-oh, I hit a button. One of these buttons will get me back. Which one is it? Should just try them all. Till we find the right one. Let me just, where am I? Right in here. There. And then those twisted wires make these bundles. And you could see like how, not to criticize us, but how low the bar was. So in the early 2000s, you could make a new nanoparticle shape and publish in Science and Nature. Then the bar got a little higher, and you had to at least they had to self-assemble into something, even though you didn't know what it was going to be. And so you could get all these different kinds of things, and then the trick is to understand what you get. He had a student who made a batch of these same nanoparticles, but he got 25% size polydispersity. And Nick said, oh my God, throw that away. That sample is, how could we possibly self-assemble anything interesting with particles that are all different sizes? So as a graduate student, one of the most important things to learn is when to listen to your advisor and when not to listen to your advisor. And oftentimes students get that wrong, but sometimes they get it right. And this time the student says, whatever, what does he know? And so he studied them, and we were astonished to find that because of the polydispersity, it led to a balancing of forces where these nanoparticles would come together and aggregate into a ball with about 300 or so nanoparticles in it. And once it got to a certain size, it was self-limiting. So you try to put another particle next to it, won't go. Take two of these big clusters, stick them together, they go right back apart. And so he got these giant clusters, we called them supraparticles, and those supraparticles were so perfectly round that they self-assembled into a face-centered cubic crystal structure. And we were able to come up with a Monte Carlo model that, that was able to explain with one model all of these different kinds of structures that are possible. So at some point, we were looking at this, and my student, Amir Haji Akbari Baloo, who is now an assistant professor of chemical engineering at Yale. So he started working on this problem. And we said, okay, I want to know which of the forces is dominant for, which of the forces is dominating to give us this and this and this. What is the relative role of all of the different attractive and repulsive forces that we have going on in this very messy system? And so I said, could you, turn off all of the interactions, just turn them off. And throw just hard tetrahedra in this box, and then just thermalize it. So that means, so we're using Monte Carlo simulations because that's really easy to do with hard particles. And the algorithm could not be simpler. You take a particle and you randomly choose a particle, and you try to randomly rotate it a tiny bit or translate it a tiny bit. Now in regular Monte Carlo, you would calculate the change in energy, and if the change in energy is negative, you do it, and if the change in energy is positive, you do it according to some Boltzmann probability. For us, these hard particles, either there's no interaction or there's an infinity of energy, because they just can't overlap. So for us, it just means if the particles don't overlap, we do it. We do the move. That's all. And so Amir did that. And then he came to me and he said, well, you should look at this. And so this is a newer simulation. I'll show you, this is Amir up here. I'll show you his simulations in a minute, but here's a box of particles, of these hard particles. And they're little dots when locally they're disordered, but this is growing into a crystal that has a diffraction pattern that looks like this. And if you count the number of Bragg peaks, and you go around, you count 12, and 12, and 12, and 12. Which tells you that this is not a regular periodic crystal, it's what's known as a quasi-crystal, which has no translational repeat unit to it, but has long-range orientational symmetry. So it is counterintuitive to most people that if you have hard particles, and they're just jiggling around in a box, and you crowd them a little bit, that they will just self-assemble from a fluid, a disordered fluid, into an ordered structure. Typically, we think of entropy. So we think of these systems as not, there's no specific attractive interaction. So why would they do such a thing? And so why they do it has to do with entropy. So let's do a little primer on entropy. And I know a bunch of you just started thermo, or some of the undergrads over here started thermo this term. Okay, so I'm sure that you're learning about the concept of entropy that was originally conceived of as from the idea of lost heat, right? So heat that energy that was lost that couldn't be used as work. But then Boltzmann and that's Gibbs, in the 1870s, were the first to connect the notion of entropy to the concept of microstates, which I mentioned before, the concept of state space. So you know what microstates are. So microstates are all the different arrangements of whatever your objects are. What are all the different arrangements in the system? So for example, if I took a snapshot of this room right now, this is a microstate. But if Jack, who's reading his phone, Provost who? I always want to do the who's on first, what's on second joke.
What's the joke?
I know. Nobody knows that, like we know it, right? Okay, I just dated myself. So anyway, if you guys switch places, that would be another microstate in the system, right? If Professor Landau moved up 3 rows, that's another microstate of the system. It's all the ways that we could fill the seats with people. Those would be different microstates. And why is that important here? So Gibbs' entropy expression says, well, if we can enumerate all of the microstates and we know the probability of occurrence of the microstate, then we can just sum them all up by taking the log of the probabilities times the probability of the microstate, just sum over all the microstates. It's just counting up all the microstates, suitably weighted, okay? And then we know the entropy of the system. Shannon entropy is something that arises, well, Shannon invented this field of information theory, and Shannon entropy is a kind of a cousin of Gibbs entropy, where the Shannon entropy measures the uncertainty that's associated with a random variable. So it's like the number of bits in a message. So the way I like to think about it is that entropy in this context is the minimum number of yes-no questions that you have to ask in order to fully determine a system. Okay, so how many of you have played 20 questions? That's it? Really? Okay, you've played? Okay, you, right in the middle. So 20 questions. So, let's see. I am thinking of a person. You know how to play. So you have to ask, you have up to 20 yes-no questions to ask me.
Okay.
So, what do you ask?
Does he have black hair?
Does he have black hair?
Or does the person have black hair?
Does the person have black hair? Sort of.
Okay. Is the person male?
Yes.
Is the person a professor?
Yes.
Is the person wearing a suit?
Yes.
Is the
Okay, we're getting there.
yeah.
So, I found it interesting that the first thing you asked about was hair color, and the second thing you asked about was
Yeah.
sex, right? So,
Probably should have been.
ideally, right, to always ask one, you always want every question to eliminate as many possibilities as you can. That way you'll get to the minimum number of yes/no questions. So an obvious question to ask is, is the person male? Then, because then you eliminate half of the population, roughly. Whereas if you ask, do they have black hair? Okay, well then you eliminate few. Okay, so that's how this works. So the minimum number of yes/no questions is the entropy if you have, two possibilities for your states, like a flipping a coin if you have heads or tails, right? So there's two possible outcomes. So there's one bit of entropy in a coin toss, right? Because I only have to ask, is it heads or is it tails? And I know the answer. I only have to ask one question. So one bit of entropy. Okay, what does it have to do with us? Well, all microstates with the same energy are equally likely. The great David Chandler used to call this a fundamental law of nature, right? That all microstates with the same energy are equally likely. And so, if you have all your states with the same microstates with the same energy, then the probability of any one microstate is 1 over the total number of microstates. Really simple. So, if you then take that and plug that into the Gibbs expression, you get the famous Boltzmann expression, where it's just the log of the total number of microstates times a factor, gives you the entropy of the system. Now, in our system, we have no energy, right? I told you that it's 0 or it's infinite, so there's no potential energy in a box of hard particles. And so the free energy of the system is just the entropy of the system, but the negative. And so when thermodynamics wants to minimize the free energy, it's really maximizing the entropy, or maximizing the total number of microstates in the system. So that means an equilibrium for a hard particle system is the maximum entropy state. That means that our system went from a disordered fluid to a quasicrystal to maximize the entropy. And that is what's counterintuitive. So this is what this structure looked like that Amir showed me. We usually think of entropy as being associated with disorder, right? And we think that things that are more disordered have more entropy. Well, that's only in the colloquial sense. What it really means is you have more entropy the less you know about the system, the more entropy you have. So here, the disorder is not in space, It's in the microstates of the system. So that means you can actually get ordered crystal structures just by maximizing the entropy. And it turns out that our quasi-crystal is isostructural to a tantalum tellurium quasi-crystal chalcogenide. And so basically that means that if you looked at where the centers of mass of all the tetrahedra are, they're sitting on the tantalum tellurium lattice sites in the atomic crystal system. And if you take our diffraction pattern, it just rotated, it fits right on top of this other diffraction pattern. So it's exactly the same crystal. One of them that's formed with, because of, quantum mechanical interactions between these atoms, and one that's formed by entropy maximization. And so this was this, so this is what this looked like, and in fact this picture, this was so unexpected and berserkous that it actually was published in the first week of the last decade in the New York Times Science section, and was for 1 week the science story of the decade. All right, so, and this picture became the BBC News image of the week in December 14th of 2009. Like usually they have like some cool picture of like a safari or some little bird, but instead they had this quasi-crystal picture, which I was super excited about. Okay, so we should not have been surprised that these hard tetrahedra should order into anything, because Onsager, same Onsager, in 1949, he said, I bet if you took infinitely long, infinitely hard rods that can't cross, and you crowded them together, that at some point they'll get stuck. What he meant was jammed, but we didn't know that word then. He said they must have to order at some point. And that's the whole basis for the isotropic nematic transition that underlies all of liquid crystal physics. And so in this simulation, this is a simulation of not infinitely long and infinitely thin, but hard rods with a long enough aspect ratio to see this effect. So when they're colored red, it means that locally they're not aligned with their neighbors, and when it's green, they're locally aligned with their neighbors. That's the isotropic nematic transition of hard rods or liquid crystals. Okay, then, so why do they do that? Because there are more ways to arrange the rods, more microstates available to the whole system if they line up than if they stay like this. So they give up rotational degrees of freedom to gain translational degrees of freedom and thereby maximize the entropy of the system. So disorder to order by maximizing the entropy. And then Kirkwood came along roughly a decade later, and he said, I bet that's true for spheres too, hard spheres. And people said, that's ridiculous. What are you talking about? There's no rotational anything. There's just translation for hard spheres. And he said, no, but they're gonna organize into a crystal structure also if they're crowded enough. And so the very first molecular dynamic simulations that were done on this system by Bernie Alder, who's in his late 90s and still working at Lawrence Livermore National Lab, and working with Wainwright, and at the same time, the same system being studied by Robert Wood and Jacobson. So one did a Monte Carlo simulation, and one did a hard particle molecular dynamic simulation. Here went from red being a disordered fluid of hard particles to an ordered crystal of hard particles, where the crystal actually forms a face-centered cubic crystal. And nobody believed this, because they said, yeah, computers, what are those? It was, like 1959 or something, so nobody believed that. They said, that's just stupid, that can't possibly be true. There are no forces, how can it order? And so there was, the colloidal crystal, the colloids community came up out of soft matter and kind of formed soft matter physics. And finally they did these experiments, Bill Russell and Paul Chitkin at Princeton at the time. They made some hard sphere colloids, and I don't know if they were PMMA or polystyrene, I can't remember, but in toluene, some organic solvent. And they flew it on the space shuttle, and so the whole crew of the space shuttle, right here, STS-73 space shuttle crew, are authors on this paper. they wanted to prove to people that if they really did eliminate all possible sources of gravity, right? So they could take these, by taking the right materials, the right combination of solvent and particle, you can density match them so it's floating, so it doesn't sediment, and you can match the indices of refraction, which remove the van der Waals interaction. So you can really screen all the interactions out and really have hard spheres. And just to show that there's really no sedimentation, they had to fly it on the space shuttle. So I don't know how much that experiment cost, but it was worth it because it finally convinced people that hard spheres would crystallize. And I just have to take this tiny digression. How many of you have been to the Yale Cemetery? You have. You know Gibbs is there, so you can go pray to the altar. This is Kirkwood's grave, and this is Onsager, and they're buried next to each other, which is interesting because they're both contributed to this. So so rumor has it that I was always told that Kirkwood and Onsager didn't get along until I visited Yale, and I learned that no. They got along fine. It was the wives that did not get along. And Kirkwood, so between the two, apparently Onsager was the one you wanted to have a beer with. That Kirkwood was more, buttoned in. And so his thing here, right, which his wife wrote, whatever bachelor's or something, PhD at this place, blah, blah, blah. Served Yale University as a Sterling Professor of Chemistry, Chairman of the Chemistry Department from this year to this year, Director of Division of Sciences for that year, all the different prizes that he won, membership in like American Chemical Society, blah, blah, and then I guess that's for posthumous awards, I don't know. And then, so then he died first, and then Onsager died. And so the inscription, if you see here, 1903, 1976, born Oslo, Norway, J. Willard Gibbs Professor, and then you see what it says right here, Nobel Laureate, etc. You cannot make this stuff up. Okay, that's the end of my digression. So now we understand that hard particles, that if we took nanoparticles and colloids, it could actually screen all the interactions, which we started doing just because we wanted to know the roles of the different interactions. Then we find out that just the shape alone and entropy can give us ordered structures. So that changed everything in the group. We just started going crazy. And I had this ambitious student from Brazil working with then postdoc Michael Engel. He's now an assistant professor in chemical engineering at Erlangen in Germany. Also, both of them physicists. They just went crazy and did a study of 145 different shapes. Like there's the tetrahedron. Where is it? There's a tetrahedron that Amir did. And then they just did what Amir did, but they did it for 144 additional shapes. And found all kinds of crystals. All of these shapes form FCC crystals, these form plastic crystals, these form liquid crystals, these all form crystals, and then there were a bunch that just didn't form any crystals. And they formed all kinds of complicated crystals, even with large unit cells. Now, so validating this in experiment is tricky, because if the particles are small, like of 100 nanometers and below, it's very difficult, if not impossible, to really screen out all the interactions. And if the particles are large, like a few hundred nanometers to a micron, then they're made a totally different way. And they're really hard to make into shapes that aren't spheres. So we've been waiting a while. There's been some experiments recently. There's one that just came out in Nature, I think, where they found this quasicrystal. And then here's an experiment from Stefano Sakana's lab at NYU that he showed at the last March meeting and gave this to me so I could show it to you, that he made these little truncated tetrahedra that Pablo predicted would form this cubic diamond crystal structure with nothing but entropy. Here's the most complicated crystal. Well, here's the largest unit cell that we've been able to get so far in simulation, just by accident. So I have a very ambitious student, Sang-Min Lee, who instead of truncating the corners of the tetrahedra, said, well, we never truncated the edges, let's do that. Through these truncated particles, tetrahedra in a box, and when it's fuzzed out, then it's just not ordered. But the box is, it's full of particles at about, I don't know, 55, 60% packing fraction. So most, so 40% or more of the box is empty. And it forms this crystal structure, which has 432 particles in the unit cell, which is ridiculous. It's so complicated. And this is the unit cell, and it's isostructural to a Birkeland-like phase that was found by Linus Pauling many, many decades ago. So that's the biggest unit cell that we found so far. So okay, it's basically the idea of Onsager. In every case, the particles are ranging so as to give you the macrostate that is consistent with the most number of microstates. That's the maximum entropy system. When you have these shapes, they do that by lining up. So it's like Onsager on steroids. So instead of having rods that line up, we have shapes, polyhedra, with faces. And if the biggest faces line up, then you have the most possible degrees of freedom, or the most possible microstates. Because this, that's all consistent with this overall crystal structure. So it's exactly the same idea as Onsager. And honestly, there are no simpler simulations that I can think of than doing Monte Carlo on hard particles. Because you're just randomly moving and randomly rotating. And you just have to check if they overlap. Which actually, to do really fast, needs a special algorithm that we stole from the graphics community. So like when SpongeBob SquarePants runs into a pole, that's the algorithm that we also use to see if two tetrahedra are going to overlap or not. Okay, sometimes the solution is even more surprising, and we see something, I don't know what to call it, I call it entropic compartmentalization. Here's a clathrate crystal that's forming out of this shape right here. It's some kind of funky shape. And it's self-assembling, and again, this is a box that's full of these particles. But to see the clathrate, we're joining the centers of the particles with these lines and then not joining particles. So then you can really see this cage-like structure. And inside the cages, we are showing the picture of the particle, but there's the same particles everywhere. But the reason we're doing that is to show you what the particles are doing inside the cages. So the particles that make up the cages are just like vibrating. And they're not really moving a lot. But the particles inside are spinning like crazy. So all the entropy goes into these spinning guys. So somehow, without any explicit forces in the system, it figures out to make this berserkest 92 particle unit cell where most of the particles really can't move very much, and a small subset move a lot, and can sample all these different microstates. And I don't know how it figures that out is a really interesting thing that we're trying to study right now. So, yeah, so kinetics. So the kinetics is really interesting. So for example, clathrates, real clathrates formed from water, form in this kind of two-step nucleation and growth mechanism. And so whenever you have like tetrahedral valence or hydrogen bonding, or like in these clathrate systems or two length scales in the system, you can get what are known as liquid-liquid transitions. So instead of going from a liquid to a solid, it goes from a liquid to another liquid. So here's an example of a simulation of the same exact clathrate crystal that Chad Merkin made with his DNA-coded nanoparticles, but here, there's no DNA. None. It's just hard particles. They form exactly the same crystal structure. And the reason is that in the DNA system, you don't have to crowd the particles, the DNA just needs to find themselves, and they'll pull the particles together. The DNA is all over the faces, so it's pulling the faces together. Without the DNA, we're crowding the particles, and the particles, because of Onsager, line up their faces. And so at the end of the day, you're getting exactly the same macroscopic effect but just different origins of these forces. And what's interesting is that it does this by first making, starting in a low density fluid, it creates a high density fluid, and out of that you get this crystal structure. And so you can see a first order phase transition from a low density fluid to a high density fluid, even before you ever get to the crystal. Here's another one I'll show you. This is one of my favorites. This is a pentagonal dipyramid. One shape, one type of particle. This is what it looks like from the top, that's what it looks like from the side. Throw it in a box, about 55% packing fraction, Monte Carlo, and we watch this crystal grow. So when it's blue, that's a particle that is at that moment in a low density fluid phase. And when it's yellow, at that moment, it's in the high density fluid phase. And when it's green, it's part of the crystal. So I'll play that movie again, because I just find this astonishing. So this is the top view, this is the side view, and this is the crystal, so one of the crystal layers. So look how this crystal is growing. It grows like a zigzag, and then turns around, right? And it's growing in this crazy way. So if I just like saw you on the street, not you, but like if I stopped you on the street and I said, look at this, what do you think's happening? You'd probably say, I don't know, those particles must be like attractive to each other in some way to come together and form that cool crystal. Except that there's no forces, there are no attractive forces. It's just the maximum entropy solution that the system on its own figures out. So I would point out, for those of you taking thermo or have taken thermo, you know the van der Waals equation state, right? Van der Waals equation state, who knows it? Who knows it? Okay, van der Waals said, okay, the ideal gas is very nice, but all the particles can sit, they're ideal, they can sit on top of each other. You can't possibly ever have a phase transition if you have an ideal gas. And you need, and van der Waals said you need two things to get a phase transition. You need, first of all, to recognize that your, whatever they are, atoms or molecules or nanoparticles or whatever, they take up space. There's an excluded volume. And so the amount of volume in the system is actually smaller than you think it is. So that's the first thing he said you have to have. And the second thing he said you have to have is an effective attraction. These are what the van der Waals isotherms look like, meaning as you're at high temperature, your pressure versus volume is monotonically decreasing. You just go from high pressure, small volume, to low pressure, large volume, one phase. And below the critical point, now you have this inflection. That means that at one pressure, you have two volumes, two phases coexisting with different volumes, a high density phase and a low density phase. If you don't have the effective attraction, I wrote effective attraction. If you don't have an attraction term, then you don't have the 1 over v squared. And without the 1 over v squared, you can't get the inflection, right? But we don't have attraction in this system. We just have entropy. So I would argue that entropy is giving rise to this effective attraction. And that's why we're able, in a one-component system, to get a fluid-fluid phase transition, which is unusual. So I argue, so someone should tell me at some point when to stop talking, because I'll just keep going and I don't know what time it is. Well, I do, but I'm not looking. The entropic bond. This is not a thing. If you Google entropic bond, you won't find anything, except maybe more papers. But I'm trying to argue that we should think about these effective, statistical, emergent entropic forces like bonds. Not real bonds, not chemical bonds, but effectively physical bonds. And just like chemical bonding is a process that's selecting for the set of interatomic orientations and positions that maximize, that minimizes the total energy among the atoms, entropic bonding is a process that selects for the set of interparticle orientations and positions that maximizes the system entropy. I can define it that way. We can calculate the energy, effective energy of the entropic bond. Like if it was an energy term, this is how much energy it would have. And it's smaller than these other much, much stronger interaction energies, but it's not insignificant. And so if you think about the chemical bond hierarchy, you have all the strong bonds, like the primary bonds, the chemists call it. Ionic bonds, covalent bonds, metallic bonds, these are strong bonds. And then you have the weaker bonds, like hydrogen bonds, van der Waals. We don't usually call them bonds because they're isotropic, but the van der Waals interactions. I think that there should also be entropic bonds on this side of this hierarchy. And I argue that other people make up bonds. So, for example, Fraser Stoddard, who won the Nobel Prize in Chemistry a couple years ago for these rotaxane molecules, like molecular nanotechnology, and the idea of the mechanical bond. He said, you know, I've got these rotaxanes, or the different pseudo-rotaxanes, catenanes. They're cyclic molecules. So I have this thing, and those are strongly bonded. And I have another molecule, and it's strongly bonded. But if they come together like that, and they're both strongly bonded, then those two are not coming apart. So what do you call that? So he called that a mechanical bond. The entropic bond is sort of like, I mean, it's not like that, but it's also not a chemical bond. But it's the idea that there's an effective attraction between these two, and there's an effective attraction between our polyhedron. And so, and we can, we see that the particles, the maximization of entropy is creating a valence that says, this is how many particles you want around you, here's what your coordination number is, here's where they should be. And we can find things that look like metallic bonding, covalent bonding, etc. So here's where, like in 5 minutes, in 1 minute, no, that's just not. Okay, so I can't possibly explain this because it's a long thing, but I'm going to tell you this crazy thing that we're doing. So my argument is, if these can be thought of like bonds, then wouldn't it be cool if there was a Schrodinger equation for these things, for these hard particle systems that we could solve and predict what should be the arrangement of these hard polyhedral shapes? Well, that's fine, but how would you do that? The Schrodinger's equation is solved for the wave function of the electron. But I don't have an electron. I don't have anything. I just have space. So what do? So I have this very brilliant postdoc named T. Vo, who is a chemical engineer. He's a theoretical soft matter physicist trapped in the body of a chemical engineer. And, which is good, because he's like applied. Anyway, so I gave him this problem. I said, this is what I think. So we need to know what's that thing, and then and how do we write a Schrodinger equation? That's it. That was my guidance to him. And then he comes back in like 2 months. He goes, yeah, I did that thing that you asked me. And the idea is to be able to replace our shapes with shape orbitals, atomic orbitals, that we can then solve. What we want to do. Here's the problem. So we're crowding stuff, and because we're crowding, then there's less space. They have to figure out what to do, and so they order. But I don't know how to write. I don't know how to express that crowding in the Hamiltonian in a way that looks like that. So I need something, like some mathematical trick. And so what he came up with, he said, well, what if we have these little ghost particles? I call them quasi-particles. And we said that two particles, they're effectively attracted due to entropy. Let's just throw in some little quasi-particles that can overlap, and they're only attract, and so the particles interact with these little mathematical fictitious quasi-particles. Because then I can write down with 70 pages of algebra an effective potential for these little quasi-particles. And then I can have a Hamiltonian that looks just like the Hamiltonians that you would use to solve Schrodinger's equation for a set of atoms. So the idea is to replace a crowded system of particle shapes that are confined in some volume to an unconfined system of shapes that are bound together through these atomic orbitals, where you're maximizing the overlap of orbitals, just like you would do in electronic structure calculation. So that's what we're doing, and I'll just mention that another thing that T did is he said, well, once we have these little particles, then we can just write down a diffusion equation for these little particles. And if you do, so you write down you end up with a Smolachowski equation, which if you do this trick that Swanson did, that he found in some book, you can make it self-adjoint, and then it looks like an eigenvalue problem. So, just to quickly, in 10 seconds, say what he did. And so then you end up with something that looks like a Schrodinger equation. You end up with this interaction between, just like electron nucleus, and an interaction between these fictitious quasi-particles and the shape. So this sounds ridiculous. I understand that. I can't believe this works. But it turns out that you can use that and calculate what these orbitals look like. You can use exactly the same matrix methods that are used in electronic structure codes to iteratively solve this eigenvalue equation. We do what the electronic structure people do when they have a trial wave function, and they take a linear combination of atomic orbitals from the different sites, and you can take like the first order orbitals. We do the same thing, but we call them shape orbitals instead of atomic orbitals. And so you can solve for what the energy effective strength of a entropic bond would be between two hard nanocubes in a sea of other nanocubes at some packing fraction. And then you can use it to look at different crystal structures. So for example, I could say what lattice is preferred for hard cubes at a density of 55 or 55% packing fraction. So I could set it up like as a simple cubic or a place center cubic or a body center cubic, and then calculate the eigenvalues of the lowest free energy bonding orbital, and see that in fact the simple cubic lattice has the lowest free energy or maximum entropy. And this is how you do, one of the ways that you do structure prediction in electronic structure codes for atoms is you place your atoms on a lattice, and then you solve this Schrodinger equation, and then you get out the energy, and then you try a different lattice and you compare that energy. Whichever lattice has the lowest energy wins. Well, that works for these systems too. And even for the tetrahedron case, we can look at this diagram, this phase diagram that my student Pablo and Michael did back in 2012, where you can take the particle, and here's when it's a perfect tetrahedron, and it makes a quasicrystal. And then you truncate it, and it makes diamond. And then you truncate it, and it makes beta-tin. And then you truncate it some more, and now it's a perfect octahedron, and you have a BCC crystal. And so he could take every shape, and as a function, and so for every shape, so here's a shape like a 0.2. He could set it up at every one of those lattices and calculate the free energy. And see that first this lowest one wins, then the purple one wins, then the orange one. And if you follow that, that's where it says the phase transition should be. And those black lines come from Monte Carlo simulations that we did 7 years ago, where we just discovered where the phase transition should be, the solid-solid transitions between these different structures. So I recognize that this is completely not understandable because it's so fast, but I'm super excited about the idea that we might have a microscopic theory of entropy, and that by casting this in terms of entropic bonds, we might have a new tool for predicting structures of nanoparticle systems, because we can build it, now we can go back and we can add in interactions into this framework. And so we might have this new tool, like the quantum guys have, for these soft matter systems. So I will stop there because I think I'm way over, and just say thank you very much. Thank you again for inviting me. It's really an honor.
We have time for questions. Yeah, Sharon.
So I gathered that the picture that you have of this entropic binding or bonding is one where you do have some localized forms of the machine. And you see the mathematical representation that sufficient to describe the system. But of course we know, for example, in the case of metallic bonds at the atomic level, that picture really doesn't work, right? I mean, copper atoms bind together to form a copper crystal because of completely localized, or almost complete delocalization of the conduction electrons. That is really what contributes provides the binding potential. So, does the analog of that exist in your in your topics?
So what I can tell you is that, for example, so we can predict the delocalized C of quasi-particles, of this delocalized bonding orbitals, whatever you call them. We predict that we've done that for like beta manganese, beta tungsten, I mean different metal systems. So we have all these shapes. We have shapes that will form a crystal structure that's also formed by metals. And by taking just the hard particles and calculating these bonding orbitals, we have to sometimes go to the second order orbital. But we can predict exactly what is seen in the atomic system in terms of it gets the right lattice. For beta manganese, for example, it's a 20 particle unit cell where 8 have one Wyckoff position and 12 have another. We predict those. We predict, what their relative spacing are, and it matches what you see in an atomic system. And we can do that with this method, which I don't know why it works, but it seems to work.
Follow-up on that actually is, what's crucial in the electronic structure calculations of atomic-based crystals is also the notion of that the electrons are fermions. For metals, you have Fermi surfaces. For conductors, you have filled bands and empty bands. What are your quasi-particles? What statistics do they have?
That's a great question. They're a mathematical convenience, right? So the properties that we assign to them is that they do not interact with each other. So we don't have like the equivalent of electron-electron interaction. They only interact with the shapes.
Well, that's the same as in density functional theory, for example.
Exactly.
Okay.
Right.
But it's crucial in density functional theory to get correct structures to build it that the electrons are fermions. So if you do DFT but treat the electrons as bosons, the world would look very different than it does look, right?
Yeah.
So, I mean, are you dealing with a multi-quasi-particle system, albeit non-interacting, or what is the structure of your model in that
Right. So I mean, that would take longer to show you, but I agree with you that there's all these things that have no analogy in my problem that from atomic systems, and so I don't know how to answer your questions. I thought I would be able to get through my whole career and not have to know about electronic structure methods, but now I have to learn. So I am looking for these critical comments to understand better where the analogy makes sense and where the analogy ends, right? Because we don't have, there's no like electron, there's no exchange, there's no coupling, there's nothing. There's just the quasi-particles mediating an effective attractive interaction between the shapes. And so the shape, I don't know how to say it, so the shape is being conveyed in the equation through these shape orbitals.
Okay. Well, I mean, you write down something like a coordinate equation.
Yeah.
As a wave function in it.
Right, so of course we don't have a wave function because I don't even know what that would mean for the system. So we have a probability density function, probability density function for the quasi-particles whose square root is the thing that's in that equation. Because there's like, I don't know how, I wouldn't use the word wave function because we don't have that, right? So it's a weird mathematical trick, I think, to do. And it keeps predicting the right things. And the way that the big trick is, how do you find the quasi-particle nucleus interaction energy? How do you do that? And that is done through a mean field calculation, where you have a reference particle in your sea of particles that's crowded at some density, and then you smear out all the other particles, right? So they're an effective field. So you don't care how they're arranged, right? So the fact that cubes form a cubic lattice does not go into the calculation of this effective potential, which is critical. Otherwise, we'd be building in the answer, right?
It just pops out that way.
Yeah.
At the end of your self-consistent mean
you do the self-consistent thing, and then, yeah. And then, that's not really the pseudopotential. The pseudopotential is a transform of that. Like the equivalent of the pseudopotential in the Hamiltonian is not quite that. It's a transform of that that makes the Smolachowski equation self-adjoint. And if you look at the transform function, it looks almost identical to the original function, so it doesn't change it very much. Anyway, it's all very new, and we're playing. So this is not all unpublished, because we're still trying to figure out exactly why this works as well.
Why don't we
Sorry?
continue that later in the
I
reception?
said, it sounds like we need to read your papers.
Yeah, well, I need to write it.
Sharon, thanks for visiting. My question actually is about this picture. Looks like you have 30 people in your group. Are they all supported by you? Are they all graduate student and postdoc? Any undergrad?
So in the picture are 25 or 6 PhD students from chemical engineering, material science, physics, macromolecular science, and engineering. There's 1 permanent guy. There's 3 postdocs, and I see maybe 3 undergraduate students.
And they're all paid by you?
Yeah, some of them have fellowships, like NSF fellowships, or Rackham Predoc, which is like 1 year, or DOE fellowship, or NDSCG from the DoD. They have those fellowships.
All right.
Yeah.
You have a question?
Yeah, and some of them maybe
One more.
from that retention package that you might have kicked into a few years ago.
Okay.
Thank you.
Question over here.
Greg Lawrence.
Go ahead.
Hi, Sharon, can I ask, I know in chemistry, temperature has a lot to do with crystallization. So would a different temperature give a different structure in your systems, do you think?
So in these hard particle systems, the temperature is irrelevant because there's no energy. There's no energy scale, right? So temperature comes in from energy per kT. But we don't have any energy, and so the temperature, all the temperature does is increase like the equivalent of the kinetic energy, so the kinetic energy of the system, but it doesn't change the energy scale.
All right.
And for us, it's just how quickly these particles are moving around, which is just how quickly they're sampling all the microstates. But what we find is a thermodynamic statement, right? So the kinetics are not important.
Okay, so second quick question, which is more important than that one. I was intrigued by the graveyard, the 2 gentlemen buried beside each other. My question is, where were the wives buried?
I don't know. Probably opposite end. Definitely on the other side.
I actually have a comment. That seems like a cemetery for computational chemists.
It's real. You can really go there.
Okay, we have a reception starting now. So if you have more questions for Dr. Glotzer, you can go talk to her. So we're going to go up the steps, make a right, and go down to the very end. There's a reception. So let's thank Dr. Glotzer for a great job.